Welcome back. So, we're talking about elasticity theory right now, and I've introduced the notions of stress and strain. We talked about field theory writ large, and in the last vignette, we talked about beam bending and the energetics of beam bending. And now, what I want to do is I want to talk about this great paper that I already mentioned in the previous vignette, which is by the groups of Cliff Tabin and Mahadavan, and is on the. It's got a great title on the growth and form of the gut, which is basically riffing on the famed book by Darcy Thompson, whose title was On Growth and Form. We just passed the 100th anniversary of that book. So, this paper, as I mentioned in the previous vignette, chooses as its topic the nature of the folds in the gut of animals such as the chicken or the mouse. And as you can see on the top in part A of this figure, so here's my plan. My plan is that I want to, bizarre as it may be, walk you through my marked up version of this paper, which I've read many times. And I want to try and give you a sense of what's in the figures. And then we'll go over to my notability, and I will try to do a few calculations that give you a sense of how the theory is done for this. Now, the thing that they do is they posit a bunch of hypotheses for what might give rise to the folding of the gut, and just to give you a sense of the carefulness of the way that they carried this work out. In part B, what you see is that they counted the number of cells, and the reason that they did this is that they were imagining, you could imagine that buckling could be induced by having more cells on top than on bottom. And so, the area taken up on the top of my little putative beam would be different than on the bottom, and that would induce bending. And the reason that they show us this figure is to reject the hypothesis of, differential numbers of cells. And for my purposes, the idea that they settle on is the coupling between the sheet known as the mesentery and the gut tube. And I think that this is best illustrated in part C. And the reason I say that is that what they do is they excise the gut tube and disconnect it from the mesentery. And what you see is that the gut tube then becomes straight. It's no longer buckled. And that's really cool and smart. It's the kind of thing that when you see it, you say, yeah, I think the evidence that you're marshaling in favor of your hypothesis is compelling. And at the top, just to come back to that on part A, they're showing us the gut folds at different levels of development. So E5, E8, E12, and all that refers to different days and development. And I don't remember the nomenclature, so I'm not going to pretend that I do. And, I apologize, but, there's only so much that I can do as I try to keep ahead of the class. And I've always made the joke, which I learned from John Whittam, that teaching is a race between the students and the professor to see who crashes and burns first. And I'm definitely in danger of crashing and burning. So in the last vignette, I told you about this little analog where they took a piece of tube and they attached it to a piece of rubber sheet, and if those two things are stretched differentially, what happens is that the system will rearrange itself. It will spontaneously fold, as you see in the picture in part B. So part B is the mimic of the composite rubber and tube. So what do I want to show you next? Figure 3 is one of my favorites, and actually there's things in the SI that go along with this. This is where the science takes place for me. Okay, I've already given my rant about surprise. I haven't changed my mind over the last 6 weeks. I feel exactly the same way I feel about it now that I did 6 weeks ago and that I did 6 years ago, frankly. And having 4 years, I'm not a Republican Democrat kind of guy, but having 4 years of alternative facts and denial of science and all that just makes me feel all the more strongly that science is about knowing what we're talking about. So that's why I love figure 3 so much, because what's here? What's here, for example, in part B, is that they're measuring the inner and the outer radii of the gut tube as a function of developmental time. Now, why does that matter? It matters because you'll remember that in the previous vignette, we had this notion of the aerial moment of inertia. The aerial moment of inertia is a statement about the geometry of the bending beam, and the stiffness of a beam depends both on what material it's made of, as mediated by the Young's modulus E, but also on the geometry as mediated by this quantity I. And so what they did in these beautiful experiments is that they actually took the trouble to, they tried to measure the inner and outer radii so that they could compute I. If you go look on Wikipedia for aerial moment of inertia, you'll find all sorts of different results. If this were a normal year for the class, as a homework, I would have everyone calculate the aerial moment of inertia by doing integrals and stuff. But I'm feeling like fatigue on the part of everyone about too many what look like gratuitous calculations. I feel like I can make everyone feel more enthusiastic about doing those calculations in the classroom setting than from me sitting in a room in San Francisco and everyone watching this on their own time back in Pasadena or wherever else they may be. Part D, same thing. They're measuring the stress and strain. So why do they do that? Because they want to get the Young's modulus. So, they just keep on doing all these clever things. So, they figure out what the strain is in the sheet. They figure out what the lengths of the mesentery and the tube are, So bottom line is that there's all this hard work that's carried out to get the quantities that are going to show up here, this equation, which I'm going to show you in a few minutes, which says that the wavelength of the instability is related to the Young modulus of the tube, the Young modulus of the mesentery, the aerial moment of inertia of the tube, which is I, and then the thickness of the layer. So, we need to know all those things in order to use the theory, in order to compute the quantities, such as the wavelength of the gut bending and the amplitude. So what I'm trying to tell you, this is me doing journal club, is I'm trying to say that this is a paper where when you read it, you say, oh, I'm going to exaggerate, but I read the paper and I say they thought of everything. They were careful. No paper can do everything. And, it's tiring when referees expect everything to be done in a paper. Nobody does everything. So for me, I look at this and I say, wow, they did a lot of hard work. They put a lot of care into getting this thing right. Maybe the picture will be amended with time. That's the way progress goes. So I'm going to come to this in a few minutes, but they then, I want to read the caption to you. They then tell us, hey, we looked at different developmental stages, and therefore we could plot on these graphs the relationship between the wavelength and the material parameters and so on. And then they also looked at different organisms. So you can see they looked at chick, quail, finch, and mouse. And all of them satisfy the scaling relationship that I'm getting ready to show you calculationally myself. So, what's the upshot? Well, I don't know, why don't I read the discussion? The developing intestine is a simple, elongated, tubular structure that is stereotypically and reproducibly folded into a compact organ through the process of looping morphogenesis. Using a combination of quantitative experiments, computations, and scaling arguments, we have shown that the associated looping patterns are quantitatively determined by the differential growth between the gut tube and the dorsal mesentery, and by their geometric and elastic properties, both within individual organisms and across species. We thus bring a quantitative biomechanical perspective to the mostly metaphoric arguments on growth and form. I love that sentence because it's true. It's metaphorical arguments on growth and form, not to take anything away from Darcy Thompson, but they've delivered. I recently wrote a piece on the 75th anniversary of Schrödinger's What is Life? And what I said is that Schrödinger has unfinished business that we need to tend to. And for sure, Darcy Thompson has unfinished business. And this is what it looks like to finish that business, in my opinion. It's really cool. So what I want to do now is I want to talk about my version of the calculations that are in the paper. So here we go. So what we're going to do is we're going to try to compare. So just to remind you of the mechanism, and I'm using the word mechanism here in a way that acknowledges that mechanism can be something other than discussing molecules. So the mechanism here is a competition between the stretch of the sheet and the bend of the gut tube. So the gut tube is growing, if you like, faster than the mesentery. And so what that does is it leads to a stretching of the gut tube. At some point, the gut tube doesn't tolerate that anymore. Sorry, the stretched sheet does not tolerate, the mesentery does not tolerate that anymore. And it says, hey, I'm going to insist that you, the tube, bend. And the consequence of that is that I will reduce my stretching energy at the cost of you, meaning you, the tube, acquiring some energy. And so the way we're going to do this is we're just going to simply balance. We're going to make a dimensionless ratio, and the dimensionless ratio is going to be bending energy over stretching energy, or stretching energy over bending energy. It doesn't matter which way we do it. We're going to set it equal to 1. And the reason we're going to set it equal to 1 is that that's going to be, in a certain sense, like the equal partitioning, the equal sharing of the energy between the bending and the stretch. This is an imprecise argument. I'm giving you a sort of hand-waving, seat-of-the-pants argument for what's going on. So what do I need to remind you of? I need to remind you that E strain is generally given by 1/2 times some modulus times a strain squared times the volume. That's the general feature of a strain energy. So let's take a look at the stretch. So the stretch is, there's a modulus associated with the mesentery. That's E sub m. There's a strain. That's epsilon, which is now squared. And then there's a volume. The volume is given by the thickness of the layer, which is H. And then we're looking at one period of the deformation. And what I'm claiming is that one period has a wavelength lambda, and the propagation of the deformation into the mesentery is of order lambda. In other words, that decay, if you go farther away from the tube than lambda, it will basically be back to roughly the flat sheet. And you can see that, in the picture here. What I'm trying to say is, if I made a very, very extended piece of tube, if I got far away, it would know nothing about the bending in the vicinity of the tube. All right, I'm not sure I said that right. So I'm saying the sheet would know, as you get far away from the tube, the sheet knows nothing about that bend. For the bending, I want you to remember E bend from last time. We said that E bend is equal to E times I over 2R squared times the length. And here, that's going to translate into this expression because the radius of curvature is of order the wavelength. You can see that from the drawing that I've given here. And so that means that I have a 1 over lambda squared, and then the length of one wavelength is lambda. And so I want to construct a dimensionless ratio. And the way I'll do that is, so, maybe I'll call that E fold. It's dimensionless, and that's going to be given by E stretched sheet divided by E bent tube. And so I can write that as EM times epsilon squared times H times lambda squared, and then that's divided by EI over 2 lambda squared times lambda. And so this thing, I can, if I do the relevant messing around, this leaves me with EM epsilon squared H divided by EI, and that is all times lambda cubed. And I want this to be equal to 1. The reason I'm setting it equal to 1 is that I'm imposing the condition that the bend and the stretch energies are comparable. And there's kind of a subtle hidden argument in there, which is that, and it's a bit like when we did the entropy maximization for the case where, for example, I had the partition which could move. And what you remember is that when the partition moved, one of the entropies went up, one of them went down, but their net actually went up until you reach the right equilibrium position. And so that's kind of what's going on here, is that we're going to, as I said before, the mesenteric sheet, when the tube is not bent, the mesenteric sheet is getting more and more and more and more stretched. And so its energy is going up quadratically with that stretch. And at some point, what I'm saying is that by putting in the bend on the tube, we're going to cost the tube, but we're going to reduce the energy stored in the strain in the sheet. And so if I write the sum of those two and minimize, that's another way of thinking of this, then I would find an optimum. So at any rate, I make this argument, and this tells me that lambda goes like E times I over EM epsilon squared H to the 1/3 power. So that's the essential scaling argument that they made, and you can see here that this quantity is precisely the thing that I'm talking about. The strain is no longer in there. That's dimensionless, remember. Okay. So anyway, I guess all that I really wanted to point out, again, I've been a little bit sloppy. You can see here that the epsilon's present in their R, but not in their lambda, and that's a more subtle argument that I'm not really making. I'm not touching. But I want you to just note that this line is the scaling argument, and this parameter is the thing that we just estimated, and they know all of the various features that are inside of that from the measurements that they make, and so they can basically lay the data points down on this graph. So I may come back and do some refinements on this story, but that's the essence of what I wanted to get across about this beautiful paper.